Okay, so today we're going to talk about, in this video, we're going to talk about exponential functions. Okay, now, exponential functions are a different family of functions than anything we've talked about so far this semester. And usually this is where we generate some class discussion about what do you think these look like and what do they mean to you. And I'm really missing this interaction that I have with you guys and gals out there. So to cut to the chase, to the punchline here, an exponential function is different from anything we've worked with so far, because instead of the x being on the ground to a fixed exponent, like y equals x squared or y equals x cubed, and the base changes, but we're always squaring or cubing something. Okay? In an exponential function, the exponent is the variable. That is what changes. So the base on the ground stays the same, and it's the exponent that's changing. Okay? Now there are some rules for b. b can't just be anything that we want. Okay? It can be a lot of things, but it has to be positive is one of the rules, because negative numbers aren't defined to any real number exponent. Also, I have to skip over 1. Okay? 1 to any power is 1. If I had y equals 1 to the x, it would be y equals 1, and that's just a line, okay? Not an exponential function. So I can pick any positive number other than 1 and be okay. Now, when we're looking at an exponential function, if we read in the paper that something is growing exponentially, for example, the coronavirus cases around the world, when we think of that growth or that decay, hopefully in our mind that we picture something that's growing very rapidly, okay, or decaying very rapidly. If I'm looking at a graph and I want to know what these functions look like, the best way that we know of to get a picture of a function, if we don't know its general shape, like all the things we talked about in chapter 2, then we're going to plot some points. So we'll pick some values of x, maybe 0 and 1 and 2, and we'll plug them in to our function, and then we'll see what comes out. So 2 to the 0 power is what? No, it's not 0, it's equal to 1. Okay? Anything to the 0 power, remember that's equal to 1. 2 to the first is 2, and 2 squared is 4. Okay? We should also pick some negative numbers, maybe -1, -2, and I'm out of room. If I have 2 to the -1 power, remember how negative exponents work. That's not equal to -2 or any version of that. Okay? That drops the 2 to the bottom and becomes 1 over 2 to the first power. 2 to the -1 power is 1/2. And so that means 2 to the -2 power is equal to 1/4. 2 to the -3 would be 1/8, and 2 to the -4 would be 1/16. So if I want to draw a sketch of this function, maybe in blue, we said when x equals 0, y is 1. When x equals 1, 2 to the first is 2. 2 squared is equal to 4. If I went to 2 cubed, it'd be 8, which is up here higher than up there in my stuff at the top that I can't draw on. Okay. 2 to the -1 power is 1/2. 2 to the -2 is 1/4, and then we said we'd be at 1/8 and 1/16. Notice that idea of growing very quickly that we said out loud a minute ago? It looks like that's the truth. Okay. Every step I take to the right, the height is going to double. So as I step from, something you guys can see that I can point with, as I step from x equals 1 to x equals 2, I went from 2 to 4. If I take one more step to the right, I'd be up here at 8. If I take one more step to the right, I'd be up at 16, which is off my board completely. It grows very quickly. Let's look at one more. And on all of these, if you need to pause as we're doing these, go ahead and hit the pause button, do some work on your own, and then come back and turn it on and make sure that your work matches what I come up with on the board. So let's do the same kind of thing that we did. And you can add 3 and -3 to this table if you'd like. So if you want to do this without me, hit pause on the video, fill in those y values, and then come back and see what we ended up with. So what we have now, 1/2 to the 0 power. Anything to the 0 power is still 1. 1/2 to the first, 1/2 to the second, 1/2 cubed would be 1/8, 1/2 to the fourth would be 1/16. Now 1/2 to the -1 power, it's going to be 2. Okay, 1 divided by 1/2, or we could flip it over and say 2 over 1 to the first. 1/2 to the -2 power is equal to 4. And to the -3 power would be equal to 8. So we're at -2, 4, at -1, 2, at 0, 1, at 1, 1/2, 2, 1/4, 3, 1/8, 4, 1/16. Okay, again, way up at 8 if we're at -3. Notice that instead of growing very quickly, in this case, it's going to decay very quickly. It's getting smaller as we go from left to right, but it also does that very quickly. It went from 8 to 4, from 4 to 2, from 2 to 1, and as I take one step to the right as we go. Excuse me. Now, for a minute, I want you to stop and think when all of our exponential functions, if we have y equals b to the x, where b has these restrictions here, okay, all of them are going to look like one of those two graphs. And when I say look like one of those two graphs, I mean have that general shape. It's either going to get bigger very, very quickly, or it's going to shrink and get smaller very, very quickly. And so to think for a moment of what situations, what I could choose for B that it would make it look like the left side over here, versus what types of things I could choose for B to make it look like the right side. And usually this is where I ask for some ideas there. But I'm gonna go to the punchline. If I have y equals b to the x, and b is bigger than 1, okay, so 1.1 or 1.01 or 1.9 or 2 or 3 or 10, okay, or 9/2. If b is bigger than 1, it's going to have this general shape where it's going to grow. It doesn't go straight up like that, but it's going to grow very quickly. As we move from left to right, it's going to go up. If I'm looking at y equals b to the x, where b is between 0 and 1. Some students will say fractions. Again, 9/2 is a fraction, but 9/2 is bigger than 1, so it's going to look like the left side. Okay. If I have a number between 0 and 1, 0.7, 9/15, 1/2, 1/3, 1/4 to the x power. Then, as we raise it to higher and higher powers, it's going to be shrinking instead of growing. So we have exponential growth if b is bigger than 1, if the base is bigger than 1. And we have exponential decay if our b is between 0 and 1. And again, it has those general shapes. Of course, if I have 3 to the x instead of 2 to the x, it's going to go through 3 and 9 and 27 instead of 2 and 4 and 8. But it's going to have that same general shape. So then the next thing that I usually do is I say pick your favorite graph. I'm going to slide this up in between. Okay, and my favorite graph is the one on the left. But we're going to look at this blue graph, which is really, in all fairness, we could use that one if you'd rather at your desk when you're working. But if I'm looking at the function f of x equals b to the x, where again b is positive but not 1, always positive but not 1. If we look at the domain of these functions, of this function, and if we look at the range of this function, and a point that it passes through. Okay, I want you to pause the video here in just a moment, and I want you to look at both graphs, both the one that's growing and the one that's shrinking, and I want you to think about what their domains are. What is the range of those graphs? What's a point that both of them happen to go through? Okay, so pause, do that, and then come back to me. Now, regardless of whether I look at this blue graph on the left, 2 to the x, or whether I look at the graph on the right, 1/2 to the x, both of those graphs go left forever and right forever. The domain is all real numbers. The range, however, not all real numbers. Both graphs go up forever, but when they go down, they only go to a certain value. And where they go is they both approach 0. Now understand that I have to have parentheses on that because there is not a value I can plug in for x and take 2 to that power and get 0. I can get really close to 0, okay, but I can't get exactly 0. Same with 1/2 to the x or any base to that power. So every number, all real numbers go in, okay, but only positive numbers come out. Okay, only positive numbers come out. I just realized, never mind, this video is going to be a little longer, but it'll be the only one. Okay. Also the point that both graphs go through, okay, because any non-zero number raised to the 0 power, b to the 0 is always going to be 1 no matter what. Okay. Now if we look at these two graphs here, okay, either the one that grows or the one that decays, okay, both have domain all real numbers, both only spit out positive numbers, both go through the point 0, 1. If I do the horizontal line test on them, notice that this function is a one-to-one function. This function here is a one-to-one function. Okay, so if my function is one-to-one, what do I know has to be true? It has to have an inverse. Okay, so I know that there's an inverse. Maybe I shouldn't use blue because blue is the way I colored it. We'll use red. I guess I'll go blind. Okay, so an inverse for this function exists. Okay, pull back up your stuff from section 4.1. What are some things we know about functions and their inverses and the relationship between the two? If I want to talk about the domain, okay, domain of this inverse function, we know the domain of the inverse is the same as the range of the function. And we know the range of the inverse is the same as the domain of the function, which means this red graph that I'm about to work with, excuse me, this red graph, we know its domain. It can only accept positive numbers. I can't plug in 0, I can't plug in negative numbers, but I can plug in anything positive. It's going to spit out all real numbers when I do that. Okay, we know a point that it passes through. If 0, 1 is on all of my b to the x graphs, then 1, 0 is going to be on all of my mystery inverse graphs. If we wanted to sketch a graph of the inverse of these functions, I'm going to sketch here on the graph that we could see. Okay, if 0, 1 is on f, then 1, 0 is on the inverse. And we know that if we fold our paper here, okay, and we blot the blue onto the other side, it's going to look like this. This would be the inverse of that blue graph. Same thing here, and I really stink at drawing these, so I apologize because this is not going to look super good. I can do the ones that grow, but not the others so much. Maybe I can kind of get it like this. Okay, oh hey, that's better than I usually do. If we blot the blue across the black dotted line, okay, we can have the red graph. This would be the inverse of this particular blue function, 1/2 to the x power. Okay. So I know a lot about this inverse. I know its domain, I know its range, I know a point that it passes through. I can sketch a graph of what it looks like. So the next thing is, let's find the inverse. Let's find the inverse of ginormous writing. Okay. If I want to find the inverse of y equals b to the x, that was my original function at the top of the page. Okay. That's what we did in 4.1. We said, I'm going to take every x and turn it into a y, and I'm going to take every y and turn it into an x. Okay, so x equals b to the y. And then what am I supposed to do with this equation? I'm supposed to solve it for y. Okay, this is where we get stuck right here. This is where we need the rest of chapter 4. If I try to solve for y, I can't use any of the algebraic methods that I've talked about so far in chapters 1 or chapters 2, any of the other things that we've discussed. I can't divide both sides by b and get that down to the ground. I can't complete the square. I can't factor anything. There is no quadratic formula. When that y is stuck up in the air, I can't algebraically solve this for y. Now that doesn't mean there's not an inverse. I know all of this red stuff about it. I can even draw pictures of it if I'm given a blue graph. Okay, but it's going to have a new name, it's going to work in a new way, and I have to understand that relationship about a function and a composition with its inverse, because the types of things we're going to have to solve in the rest of chapter 4, we can't do that using I'm going to say the normal methods, the things that we've done up to this point. Okay. So there is more to section 4.2, but this is all I'm going to talk about initially. Okay, we'll come back and revisit it at a later time. Okay, sorry this video got kind of long.